In this short video, we will look at some properties of surface tension. We'll introduce what surface tension is. We'll apply it to capillary action, and we'll do so at a level that's appropriate for a general chemistry audience. Okay, so let's have a look at surface tension. Let's get the pen working. Surface tension we will call gamma. Surface tension gamma, and we know what surface tension is qualitatively. It's that feature of liquids, for example, or it's possessed by liquids that have intermolecular forces that pull neighboring molecules together and prevent easy passage through that liquid. So, for example, a water gliding insect or a mosquito or any other lightweight insect could easily walk across the surface of water because the mass of the insect in the gravitational field of this planet is not enough to generate enough weight to force the molecules of water apart, and so the water instead keeps the insect above its surface. There's an equation that's going to be useful here. I'll write it, then we'll see what it means. Work is equal to surface tension change in sigma, where sigma is surface area. Okay, so let's interpret what this equation means. If you want to change, let's interpret it backwards. If you want to, and let's get a red, see if I can activate the red pen here. If you want to change the surface area of a liquid, and that liquid has a surface tension, you're going to have to do work on that liquid. So that would be the way I would interpret this equation. I would interpret it backwards if you wanted to translate the mathematical presentation into a more standard written representation. Okay, let's go back to our black pen. Okay, so importantly, if we ignore the surface tension for a minute and we just focus on the surface area, we know that work has units of energy. We know that work has units of energy. So let's have a look. Work has units of energy. And the energy that we're specifically interested in here is Gibbs free energy. Okay, so we are interested here in Gibbs free energy, and you'll see why in a second. Gibbs free energy, work has units of energy. So I'm going to say dG, specifically the change in Gibbs free energy, that's where I'm going to be interested in. And we'll see why in a second. We're going to use some powerful language. So we can therefore, let me just push this up a little bit. We can therefore say that positive work, because you can do work on something or something can do work on you, but positive work is proportional to positive change in Gibbs free energy in terms of units at least. So this implies, if we go back to our original equation, this implies that a positive change in Gibbs free energy is proportional to positive surface tension and change in surface area. Okay. So far so good. We've made some reasonable assertions. Let's start to see the consequences of these assertions. We know from thermodynamics that spontaneous processes have a negative change in Gibbs free energy. So what do I mean by a spontaneous process? A spontaneous process, I essentially mean a process that's possible, a process that will happen, independent of any extraneous pressures or forces imposed upon it. So something that just naturally will happen. That's what I mean by spontaneous. Don't know when it'll happen or how fast, but it will happen if given enough time to play out. Okay. So if we take that into account and go back to our process here now, then we have, well, first of all, we can see that we're saying that a positive dg is proportional to a positive d sigma, change in surface area. So up here, we had the positive by this product here. So that positive, there was no negative anywhere, so that positive can apply to the surface area, which really is the only thing that can have the option to have a negative value, right? Because the change can be a positive or a negative change. Okay. So this therefore implies that a negative change in Gibbs free energy, which is the spontaneous one, would be proportional to a negative change in surface area. So if we look at this expression here, what we've learned is that this is the spontaneous change. So we can say that surface tension gamma causes a spontaneous contraction. So importantly, the way we're presenting it here, there's a contraction force that's spontaneous, and that's because we have this negative change in Gibbs free energy related to a negative change in surface area. Well, if surface area changes in a negative way, that means it's trying to pull in on itself, so that's a contraction. So that's why balls of water, droplets, form droplets to begin with, because the molecules in the water, when it becomes a certain size, they're trying to contract their own surface area, and so you get this spherical beading. So that's one important thing. And we know to link this with intermolecular forces, which we've seen earlier on. We know that the the contraction occurs via attractive intermolecular forces. Attractive intermolecular forces. Okay, so we've got at least some kind of a semi-quantitative, well, quantitative, we just haven't put numbers in yet, but we've got some kind of way to think about the contractive nature of surface tension, and we can see how it executes that contractive nature via intermolecular forces. Let's look at an example, a useful example of surface tension. Let's look at capillary action. So let's get that out the way. It just won't. For some reason it just does not want to let me get that out the way. Okay, well maybe we'll just keep writing. So let's look at capillary action. Okay, capillary action. And for capillary action, we're going to use the Young-Laplace equation. Young-Laplace equation, which essentially is pressure on the outside of a spherical droplet, if you like, is equal to the pressure on the inside plus twice the surface tension over the radius of the droplet. Okay, so this is our Young-Laplace equation, which we're going to use. So let's start to frame this in terms of a diagram. So I'm going to get my best artistic skills to play here. So let's look at a capillary tube. A capillary tube is just a thin tube. Oh, don't know what I did then. So let's say that's a pretty good capillary tube. Let's say the liquid has risen up inside like this. Let's start to annotate this diagram a little bit. So let's say, if I push this up a bit. Let's look at this level of water here, which I really didn't do a good job of drawing that. There you go, I want to hit that. Okay, so let's say that we have obviously a pressure here, pushing the surface of that water up. We have a pressure here, pushing the surface of that water up. The liquid, if we look at the bottom of the meniscus here, the water has risen a height h. Above the surface of the bulk water. So imagine this is a thin glass tube, and water has risen up. There's going to be a pressure trying to get inside, but there's also a pressure matching it trying to get outside. Okay. Pressure trying to get inside, pressure trying to get outside. And you could well imagine that this, you could imagine a continuum of this meniscus as a pseudo sphere like this. So if this were a sphere or a droplet, this P out here would be the pressure trying to get out of this droplet or bubble, and this P in would be the pressure trying to get inside. Okay, so if we're oriented, we have a framework, we know what P out and P in is. Okay, I could probably add a few more labels of pressure here. I'll try not to do too much, keep it tidy. Okay, so that's our basic setup. Let's start writing some things about it. Maybe you can put it over here. Okay. So we can say when the volume of the liquid is risen, when the volume of the liquid has risen a height h above the surface of the bulk liquid, as a result of capillary action, so when the volume of the liquid has risen a height h above the surface of the bulk liquid as a result of capillary action, comma, we can say at that time that P out is equal to P in. And we know that because if it were not true, then the height would be dynamic. And right now the height is a fixed value. You can measure it, it's stable. All the extraneous forces have matched. So we can say that P out equals P in. And we would have in our, our pseudo bubble here, we only see the bottom of it. I've added a dashed line here to make it look like a bubble. The radius of that bubble would be fixed. Actually, the radius would be fixed anyway. But more importantly, the height is not changing. That would be a better, clearer way to think of it. The height is not changing. Okay. So if we assume that P out equals P in, we also have to acknowledge that the mass of the elevated liquid in the capillary tube well, that's going to be acted on by the force of gravitation. Is acted on by gravity and we know we're just going to look at Newtonian gravity here. So we know that force is mass times acceleration, where if we're interested in gravity, then the acceleration is g, caused by the acceleration, gravitational acceleration of our planet. We know from our pressure discussions in other videos that pressure is force per unit area. And so we can start to insert force into our pressure equation. So we know that pressure is the mass of liquid, the gravitational force of our planet, over area. We can also say that this is equal to mass times the gravitational force of our planet. And I can write height as a numerator and volume as a denominator. And I can do that because the one dimension of length in my height here would cancel one of the 3 dimensions of length in my volume here and would return again to my 2 dimensions of length in my area. The nice thing about doing it this way is that we've now got a way to incorporate density, where density is mass P in a volume. So this is density, which I'm going to give the symbol rho. So we can write this as rho GH. So I've incorporated, not only do I have pressure, an extra pressure term, but I've got pressure in terms of the density of the liquid and also the height of my capillary action. So that's a nice expression. Okay, so let's go back to our Young-Laplace equation and see where this would fit in. Which direction would this pressure be? Well, this is going to be down, right? So if we look at our equation, not our equation, sorry, our diagram, this extra pressure, this pressure caused by the extra liquid being elevated and apparently being opposed by gravity, this extra pressure would be in the same direction as P out. So let's go ahead and rewrite our Young-Laplace equation incorporating this extra pressure. Okay. So if we had originally P out is equal to P in plus twice the surface tension over R, the radius of the capillary tube, then this extra term, this extra pressure term, is definitely going to be in the same direction as gravity, which is in the same direction as P out. So we would naturally add it over here. So this is going to be rho GH. Okay. So we've added this extra term here, and we've slotted it in here in our new updated version of the Young-Laplace equation. Now, recall something we said earlier. Earlier we said that when the capillary action is played out, P out is equal to P in. So if we now consider that here, then the P out and the P in just become common terms to both sides. So I could just go ahead and cancel them. So I'm left with rho GH, density, gravitation, height, is equal to twice surface tension over radius of capillary tube. The nice thing about this is now I can solve for surface tension if that's what I wanted to do. Surface tension is the density of the liquid, gravitational field that the capillary action is happening in, height capillary attains, radius of the capillary tube, all over the number 2. So that's a nice simple equation, and this is one way that you could essentially fabricate a capillary tube, put an unknown liquid in, and you could quickly measure the height of capillary action and ascertain the surface tension of the liquid. Okay, so this is great. Let's plug some numbers in and let's actually do a question. Okay, so let's actually look at a question, and I'm going to call this capillary action question. Capillary action question. Okay, so we're told that water rises, let's say 7.36 centimeters at 25 degrees Celsius, through a capillary tube, of radius 0.2 millimeter. Calculate the surface tension of the water. Okay, so there's our question. Let's look at our answer. Okay, so we're going to use our equation. Surface tension is rho g h r over the number 2. Okay, now let's plug in some numbers. Do a little dimensional analysis here. So I can just set up some values here. I know that 1,000 kilogram is equal to 1 meter cubed. So I'm just assuming an average density of water here. So there's definitely an assumption. So this would be rho, density of water. Now this can fluctuate. You know, the exact density of water at 25 degrees is not exactly 1,000 kilogram per meter cubed, but it's an approximation. I know that 9.8 meters is the distance traveled in 1 second squared. That's the acceleration. That's g on this planet, 9.8 meter per second squared. I know from the question I've got, what do we have? I can't see the question anymore. Yeah, I had 7.36 centimeter. That was the height. So we need that in meters. So we've got 7.36 by 10 to the negative 2 meter. That's our height. And then the radius I need also in meter. So I was given 0.2 millimeter. So that would be 2.0 by 10 to the negative 4 meter. And that's our radius. And then I need a denominator 2, so I can just put 1 over 2 here to get a 2 down in the denominator. And if you run this through, this would roughly give me 70 millinewton per meter, where recall from your physics classes that a Newton is a kilogram meter per second squared. They really must stop putting buttons on these stylus pens, because every time you grip the pen you press a button. Okay, so there's a genuine out the tin calculation, capillary action, the likes of which I want my students to be on the lookout for. Can't speak for anybody else's students. Okay, so we applied some numbers. Nice little question. Obviously all the hard work was done as soon as we knew this equation. So in summary, surface tension is a spontaneously contractive force. It operates via intermolecular forces, and we can plug some numbers in and we can quickly see a great application of surface tension is capillary action. And we are done and dusted in 30 minutes.